implies it's irreducible
Oh,
in an
not
integral domain.
Okay.
So, in other words, we can negate this and get the contrapositive, I think. Anyway, so it doesn't, the last example actually isn't, I was thinking I could go back to the last example and say, aha, well z adjoining the square root of -3 is not an integral domain, apparently, but I can't say that. I better not say that, because I said in the context of the last example, it's an integral domain, didn't I? So, I do think it is. Anyway. All right, so let B be a commutative ring with identity, and A and B are associates. Well, if you have associates, they generate the same ideal. All right? My laser's a bit much. Maybe I'll go to a more low-tech solution. Yeah. So if you have associates, they generate the same ideal, right? And if R is an integral domain, and I is equal to A, then any other generator of A is. So in other words, if you want to know what are all possible generators in an integral domain, you just have to look at associates. All right, so for example, the thing I've covered up with the board right now, but in the Gaussian integers, right, if you looked at the ideal generated by 3 plus 2i, there's 3 other choices you have. Because there's only three different associates for a given non-zero Gaussian integer, right? Like -3, minus parentheses 3 plus 2i, or I times parentheses 3 plus 2i, or minus I times parentheses 3 plus 2i. All 4 of those elements generate the same ideal in the Gaussian integers. That's a consequence of this theorem. I'll let you guys read the proof. It's not especially exciting. It's really just straight arguments on the definition of, associates and how we define ideal generated by an element and such. So what about when the ring's not integral? Is it possible that, you have in a not an integral domain, can you have the ideal generated by A and the ideal generated by C the same for things that are not associates? Well, for example, I thought, I could look at Z6, right? That's not an integral domain. That's my go-to not integral domain. If you've been paying attention, that's what I always look at. I said, are 2 and 4 associates? Because like the ideal generated by 2 and the ideal generated by 4, well, they generate the same ideal, 0, 2, and 4. But the thing is, I think they are associates in this case because 2 times 5 is 10, which is 4 mod 6. So that shows that 2 and 4 are associates. So that doesn't, it can be true when we don't have an integral domain. So this shows that the second part of that theorem can be true outside the context R as an integral domain, but for a non-example, in other words, outside the context of an integral domain where you have an ideal which is generated by 2 elements, and those elements are not associates, you have to go for something more exotic. And if you click this link, you can see it. If I have added a link to a math stack exchange discussion for a counterexample, you can rest assured it's something ugly that I didn't feel like typing up. All right. Theorem 4.710. In a principle, a PID, an element is prime if and only if it's irreducible. Aha. Well, this is interesting. So what was the previous one? In an integral domain, we said in an integral domain, prime implies irreducible, right? Now we're saying in a principal ideal domain. What is a principal ideal domain? It's an integral domain in which every ideal is generated by just one element, right? They could be different elements for different ideals, but like for a given ideal, you can write it as being generated by an element. It's a principal ideal. Okay, so here's the proof. First of all, the forward implication is already given to us by the previous theorem. All right, prime implies irreducible. And that one we actually worked out, right? That's the last thing I wrote on the board carefully. Now the other direction, check this out. Conversely, suppose suppose an element's irreducible, all right? And I've seen this construction used in a lot of different things. They construct, suppose A is irreducible, and suppose A divides BC, right? We'd like to show that either A divides B or A divides C to show that A is prime, right? So I define the ideal generated by D linear combinations, if you will, of A and B. So I take X and Y elements of the domain, and A and B here are this A and that B. Okay. You can show that it's an ideal. I think that's what I do next, actually. So I pick Z and W in the ideal. I show that the difference of things in the ideal is once more in the ideal, right? And what else do I need to check to show it's an ideal? The Uber closure, right? So I should take an arbitrary element of D and like multiply it by Z and show that it's still in there. Let's see how that goes. There it is. So like R times Z is R times AX plus BY, which of course is ARX times BRY, but this is in D and that's in D, so therefore this is an I by definition. So I is an ideal, right? What's the context here though? We're working in a principal ideal domain. That means that this ideal can be generated by some element. And that's what's going to give us what we need. So since I is an ideal, and it's a principal ideal domain, there exists D, for which we have I is generated by D. But notice that A is an I, so that means A is equal to RD, right? But since A is irreducible, we have what? Either R or D is a unit. Okay, and then, so two cases, right? If D is a unit, then 1 is equal to dd prime for some D prime, which shows you that 1 is an element of the ideal, which means that 1 is equal to AX plus BY versus X, Y, and D, right? And so you can take this and multiply by C to get this, which then shows that A divides ACX. Well, I mean, that's just obvious. And we assume that A divides BC. So let's see here. We have A divides BC, right? A obviously divides this. So if you have A divides this and A divides that, it follows that A divides C as well by properties of divisibility, right? If it divides both things being added together, then it divides the sum as well. That was one of our basic theorems on divisibility. Therefore, A divides C, which is one of the possibilities we were looking for, right? The other possibility was that A divides B. We'd like that as another possibility. Now, the other case is that R is a unit. Remember, either R or D was a unit. If R is a unit, then A equals RD provides that A and R are associates, and the theorem that I didn't go through the proof of, but I projected here, says that this and that are equal. Hence, the ideal is generated by A, so B is equal to this. You find B is equal to A lambda, which shows you that A divides B, which was the other possibility. So in other words, we've shown that irreducible implies prime. But this was in the context of a principal ideal domain. So which examples that we work with are principal ideal domains? Well, apparently, now we can say something about Z adjoining the square root of -3, right?
PID.
It cannot be a PID because we found a prime which was not an irreducible, right? This theorem says in the context of a PID, prime if and only if irreducible. So like the prime elements and the irreducible elements are one and the same. And in fact, the integers, Z, are a PID. So every integer, every ideal of the integers, you can prove this. And it's actually kind of, I usually end up proving that at some point in this kind of course, and it just doesn't happen for us. I don't know how it didn't happen. It didn't happen, but you're like, I guess you should put that on the final, right? We just stop that. So if you want to prove that every ideal is principal in Z, what you do is just take, suppose you have an ideal of Z, well then you've got a subset of the integers, right? And then you can look at the positive elements in the ideal, all right? And then you can apply the well-ordering principle, right? And then you can make an argument that the smallest element actually has to generate everything. In so doing, you can prove that every ideal in the integers is principal. In other words, every ideal in the integers has the form nz. So this is good news because that means that irreducible and prime integers are one and the same, which is why we were able to, make the definition that we made. It doesn't violate the usual definition because they're equivalent in the context of the integers. All right. So polynomials are a principal ideal domain, right? So we also have that. So in the context of polynomials and polynomial factoring, prime and irreducible are also interchangeable if we're talking about polynomials over a field. Because if the field, field coefficients, polynomials, f of x as it's called, this is a PID, so in that context, irreducible and prime, one and the same, all right? So that's happy. And it also helps you to understand why the distinction in these concepts took abstract algebra a little while to unravel, right? Because they're so intertwined in most of the usual examples. So I mentioned here, Gallian provides the example of, so Zx, this is polynomials with integer coefficients. This is an ideal, which is not principal. It takes two things to generate it, and there's no way you can find just one thing to generate this ideal. That proves that Z adjoint X, the polynomials with integer coefficients, is not a principal ideal domain. So it is though an integral domain. We have argued that if you take an integral domain, you look at polynomials over an integral domain, you still get an integral domain. All right, so next lecture here, 28, I then begin to talk about what are called Euclidean domains. All right, so it's a Euclidean domain if you can find a norm on the space such that you have Euclidean, like basically division algorithm. So if you have A and B with B non-zero, you can find a quotient, you can find a remainder, and such that you're within, basically the remainder has to be small as is governed by the norm, all right? And that's it. Now, we've talked about this before, so there's some material here that I'm going to kind of skip over a bit. All right, so I talk about the non-uniqueness of the remainder here, which we talked about before. I point out that polynomials over a field are Euclidean domain because you can define the norm to be the degree of the polynomial. That's new for us, all right? The degree of the polynomial plays the role of norm. So that's interesting. And the units, so we said that norm 1 is units. In the context of polynomials, it's norm 0 that are units. So like non-zero constant polynomials are the ones that have degree 0, those are the units for the polynomials. So not everything is the same for like a general norm as it was for the specific norm we looked at, the ones on the algebraic, like z adjoins the square root of plus or minus d, but there are similarities. Of course, we talked about the Gaussian integers before, right? Those are a Euclidean domain. We've even looked at how to actually achieve the division algorithm there, right? Here's details about that we've gone through before. Here's something you guys almost did correctly in the homework.
Thank you.
Well, there's always the final. Let's see here. And then, one thing I should mention, if we have the sum of ideals, you can add ideals together. That's just defined by like adding together. If I add two sets, we just take all like finite sums. You just take it like, if I have a set A and a set B and I add them together, I can say like it's x plus y, where x is from A and y is from B. So like that's what's meant by adding these two ideals, just like sums of things from here and here. And so in the context that the greatest common divisor of two Gaussian integers is a unit, it then follows that when you add these two ideals together, you get everything. So such ideals are said to be co-maximal. So co-maximality of ideals is the ideal version of like relative primeness. Two integers are relatively prime if their greatest common divisor is an integer. So if you add together two ideals and you get the whole thing, that's kind of the same idea. You notice we've just defined the word prime and irreducible, prime for ideal, but we've also defined prime for element. We've also defined irreducible for element. Now we didn't call it an irreducible ideal, right? We called it a maximal ideal. But there's some kind of interplay going on between elements and ideals here that we're trying to get at.
Is because this looks so like since we're rediscovering like really niche things about like abstract algebra topics, is that why number theorists went into like more abstract algebra, because they started seeing so many connections and patterns over what they were already studying?
I think so, yes. I think that's a good explanation of what happened. They studied some very hard problems and they found patterns, and then they wanted to explain when those patterns happen in the most generality they can, and that led them to the project of abstract algebra. That's one way to look at it. In fact, so if you guys don't mind, I really would like to finish.
Yeah.
I need about 10 minutes, is that okay? So I mean, I'm being very Machiavellian in my lecturing, do your evil all at once kind of thing. But so in this paragraph here, I explained the story I've told you before in part, and I'll return to it again, but basically the story is, that Euler and Lagrange were already working with algebraic integers, things like Gaussian integers, which is kind of an ironic name because Gauss is actually, in some sense, more responsible for going away from those kinds of arguments, like his disquisition arithmetica. Did all of these things with modular arithmetic, and he basically did not use all of these fancy algebraic number systems like we've seen Gaussian integers give us all kinds of really cool arguments about primes of the form, 4n plus 1 or 4n plus 3, right? They've given us tremendous insight into the sums of squares and how they can fit into a certain prime element. And those kind of arguments exist as well for other kinds of primes in terms of other number systems. And but Gauss didn't invest that much into that kind of thinking because he knew the problem with unique factorization, right? He knew that over certain number systems we lost unique factorization, which ultimately seduced people like Lamé into making a false proof of the Fermat's last theorem, because it was based on unique factorization of what are called cyclotomic numbers. And anyway, long story short, eventually to fix those things, you have to work with ideals rather than numbers, right? That's where we're heading for. It'll be after Thanksgiving when we get there, but it'll be like the last thing we talk about. But anyway, so ultimately the work, Lamé's false proof was sort of illuminated by Kummer and his introduction of ideal numbers, which is basically elevating ideals to numbers in a certain way. And that was then fleshed out by Dedekind. And then Dedekind was the inspiration of Emmy Noether. Emmy Noether is well known for saying, it's all in Dedekind. Like that's something she always told her students. Like everything that we're doing, it's already in Dedekind's work. But this sells short the contributions of Emmy Noether. Is arguably where abstract algebra in its modern sense really started, is in the work of Emmy Noether and her students. You could argue that.
What year?
1920s, somewhere in here. She died somewhat young from complications to a surgery or something, if I remember right. Otherwise, her name would be much more large, much larger in the story. But anyway. So here's the definition. If you have an integral domain, a unique factorization domain, or UFD, it's every element, non-zero element of the domain can be written as a product of irreducible elements. And in that context, the uniqueness, and I really like the way the uniqueness is written. We've struggled with the notation for this. This is a really slick way to capture uniqueness up to reordering. So uniqueness up to reordering, if you can write x this way and you can write x that way, then you can take all of the y's, and they're like units times the x's. So no, like, you can shift them around. There's some way that they have to line up. All right, so in other words, two factorizations into product of irreducibles, all of those factors in the products, they have to be associates for the other factoring of it. They're all associates. See, y1 is an associate of some x in here. And then this is where this is where it gets, this is no other ascending chain condition in a PID. In a principal ideal domain, any strictly increasing chain of ideals, I1, I2, must be finite in length. So that seems like kind of a weird thing to say, right? Like, what does that even mean? Well, the proof kind of explains for you. So if you have a chain of strictly increasing, which means that these are strict inclusions, right? They can't be equal, okay? And this is all happening in a principal ideal domain. Well, then here's the sneaky thing. If you take the union over all of these, you can prove that that's an ideal. Right? I don't actually have the details here, but you can take it for a spin, take the difference, test the overclosure. You'll be able to prove that that's an ideal. So if it's an ideal, we're in a principal ideal domain. That means we can generate it by some element D. All right. So since D is in I, that means D is in IN for some n and n, right? But notice that every I is contained in I. Every I sub I is contained in I, big I, which is D, which means that wherever this D is found, that has to be the terminal ideal. You can't go past that because we have this strict inclusion. It's like if you went past it, you would have something that wasn't generated by D that was in the next one, which would be forbidden. We can't do that. So it has to stop at IN, the terminal ideal. All right, so if you have strictly increasing chain of ideals, it has to be finite in length. Now, you might wonder what on earth this has to do with unique factorization, right? If you're like me, when you first read these arguments, you're like, what on earth does this have to do with unique factorization? Well, here's how it goes. Theorem. Every principal ideal domain is a unique factorization domain. So here's how the proof goes. Number one, you show that a factorization contains at least one irreducible. Number two, you show that a factorization of a sub 0 into a product of irreducibles, there is a factorization. And number three, you show uniqueness up to associates. So here's how it goes. So we're assuming that A naught is not equal to 0, and A naught is not a unit, all right? So that's the presupposition of like factoring. We're only factoring things. We're interested in factoring things that are not 0 and not units, okay? All right, so not a sub 0 is not 0 and it's not a unit. Now, if it is irreducible, we're done. We've shown that it's factored into an irreducible. It is its own factorization, right? If it's already irreducible, we're done. Otherwise, a sub 0 is a sub 1 times b sub 1, right? Where a1 is not a unit and b1 is not equal to 0. Now, if a1 is irreducible, then we've shown that a sub 0 contains an irreducible. That should be a sub 0. Otherwise, suppose that a1 is equal to a sub 2 times b sub 2, where b sub 2 is not equal to 0 and a sub 2 is not a unit. And we can continue this in this fashion, and define a sub n plus 1 not a unit, and b sub n b sub n plus 1 not equal to 0, for which an is an plus 1 and bn plus 1. Continue in this fashion. So notice that because this is equal to that, that implies that the ideal generated by a sub n is contained in the ideal generated by a sub n plus 1. And they're not equal, because these are not associates. By assumption, by construction, they're not associates, and therefore the ideals are not equal. That's this associate theorem. And so what we have then is an ascending chain of ideals. has to terminate by the ascending chain condition. And that implies that a sub 0 can be written as r times a sub k, therefore a sub 0 contains an irreducible. So to me, this is an exceedingly sneaky argument. I would never have thought of this in a million years, for sure, you know? And then like 2, once you know that a sub 0 is irreducible, so there is an irreducible P1 and a non-unit such that A0 is P1, C1. C1 is irreducible, then we have factored it into irreducibles. Otherwise, the non-unit C1 can be factored into a product of things where those are not units. And so again, you've got ascending chain of ideals, a sub 0, P1, P2, da da da. And the ascending chain condition, it must terminate at P sub t, which then shows you that by the construction of the chain, we find that a sub 0 is the product of these irreducibles. So, yeah. So what makes all of these ascending chain arguments happen? It's that we're in a principal ideal domain, right? So the principal ideal domain was critical to the ascending chain condition proof. So, and then I'll spare you the proof of the uniqueness in 3 if they're to look at, but I just want to get to the point here. So what we have then is we have the proof that PID implies UFD, right? And down here, so what corollary to that? Well, if you have a field, polynomials over a field, that's a unique factorization domain. How do I know that? Remember, we know that polynomials over a field are a PID, but PID implies UFD. Done. So that's why we have unique factorizations of polynomials. That's an incredible result to have as a corollary. Every Euclidean domain is a principal ideal domain. Now this is not a consequence of the UFD thing we just looked at. But if you study the proof here, it's just like what we gave. It is very close to things we proved before, actually. But I just want to point out to you what this theorem says, and you know, if you guys want to, we can look at the proof of it next time or whatever. But I would just like you to just notice what it's saying. Euclidean domain implies principal domain, right? So we know Euclidean domain implies principal domain, implies unique factorization domain. But these implications are not reversible.
So if you have a UFD, you don't necessarily have a Euclidean domain.
UFD does not necessarily imply PID. PID does not necessarily imply ED. Although no one uses the abbreviation ED for some reason. So. Every Euclidean domain is a unique factorization domain. Here's the counterexamples. So polynomials with integer coefficients are a unique factorization domain, but this is not a principal ideal domain because the ideal generated by 2 and x is not a principal ideal. All right, so that's the example of UFD does not imply PID. One example, there are others. It is much harder to come up with an example of PID does not imply Euclidean domain. All right, and so you can click on this link for the. It's much harder because the definition of Euclidean domain is much slipperier. How we define Euclidean domain? Well, there's this norm, and it behaves in a certain way. How do you prove the non-existence of a norm on some space? See, yeah, right. And then, let's see here. Un momento. So this is the last page in this lecture, and here, oh man. So here, you'll get a proof of Eisenstein's criteria. Remember we used that? Now, guys, something I was worried about, did I say p squared did not divide a sub 0 when I talked about it to you in class? I haven't had a chance to go back and review I feel like I might have dropped that when I copied it down, but that's an important condition that I have neglected, I think, when I talked to you guys about Eisenstein's criteria. So what you need is that p does not divide the leading coefficient, then p divides all of the next to leading coefficients all the way down to constant. However, p squared does not divide the constant coefficient. I think I failed to say that. Now it was true where we applied it, I'm pretty sure, but anyway. So anyway, here I'll let you guys read this, but it's quite understandable. This is a proof that you know the Eisenstein criteria using that's couched in the results that we currently have. You can understand this proof. It's not that bad actually. One of the critical things is that because you're reducing, so like polynomials are not a UFD, right? Polynomials over Z is not a unique factorization domain. But when you make the reduction to like mod P polynomials, right? If you reduce the coefficients of an integer polynomial to Z mod P, then all of a sudden you're working with polynomials over a field. So you can, it's a UFD, and so like this is like the reduction ends up being this, and because it's a UFD, you have that either X has to divide that or that, and that basically you end up forcing the p squared divides the constant, which is contradicting the assumption that it doesn't.
You said p squared has to divide a naught?
P squared must not divide a naught.
You didn't put that.
I thought I didn't. My bad. I was.
Yeah.
Yeah. Shame on me. But anyway, and then there's this example. So what I wanted to get this done with, because I wanted to start on extension fields for you guys next time, because it's something I'd like to spend a lot more time on. I mean, these are important things to know about that I'm telling you, but they don't really. Well, they're important.
Is it just me or are we talking